Today, we are cracking a really cool chemical code. We're going to figure out why some chemical reactions get piping hot while others get shockingly cold. Let's jump in.
So think about this for a second. You crack open a hand warmer, give it a shake, and boom, it gets all toasty. But then you snap one of those instant ice packs, and it gets freezing cold. They're both just simple chemical reactions, right? So what's the deal? What is the fundamental difference? Well, that's the mystery we are going to solve.
Okay, so the first piece of the puzzle is realizing that all chemical reactions, every single one, fall into two basic camps when it comes to energy. They either spit heat out into the world or they suck it in from their surroundings. And of course, these two camps have names. On one side, you've got exothermic reactions. The easy way to remember this one is that heat exits the reaction. It escapes, making everything around it, like your cold hands, feel warmer. And on the other side, you've got endothermic reactions. Here, heat energy has to enter the reaction. It pulls heat in from the surroundings, which is why that ice pack feels so cold.
So where is all this energy coming from or going to? Well, the secret isn't really about the chemicals themselves, but about the invisible glue that holds them together. We're talking about chemical bonds. At its heart, every chemical reaction is just a story about old bonds breaking apart and new bonds being put together.
And here's rule number 1 of our energy code. You always have to spend energy to break a bond. Always. Think of it like a business investment. You've got to put some energy capital in just to get things started, to snap those connections apart. This part of the process is always endothermic.
Now for rule number 2. When new bonds form to create the final products, energy is always released. This is your payout. It's the profit you get from making those new, stable connections. And this part is always exothermic. So every single reaction has this two-sided coin, an energy cost and an energy payout.
And that brings us to the most important part. Whether a reaction feels hot or cold in the end just comes down to a simple question. Which was bigger? The energy you had to invest or the energy you got paid out? It's really just balancing an energy budget.
So it all boils down to this one simple formula. The total energy change is just the energy you put in to break the old bonds minus the energy you got out when the new ones formed. This little calculation is the key to cracking the entire code.
Let's look at an exothermic reaction again, like our friendly hand warmer. In this case, the energy payout you get from forming the new, super stable bonds is way bigger than what you had to put in. The final products are at a lower energy level, and all that extra energy gets released as heat. That's why the overall energy change has a negative value.
Now let's flip it for that endothermic ice pack. Here, it costs a lot more energy to break the original bonds than you ever get back from forming the new ones. The products end up at a higher energy level, and to make up that difference, the reaction has to literally pull energy from its surroundings, making everything around it feel cold. That's why the overall change is positive.
You know, we can actually map this whole energy journey out. We can visualize it using something called a reaction profile. It's basically an energy graph, kind of like a roller coaster track, that shows the energy level at every single stage of the reaction.
But there's a little catch. Even a reaction that's just itching to release energy needs a little nudge to get started. You need a little push to get over the initial hump. And that push, that initial energy barrier, has a name. It's called activation energy.
So here's what that map looks like for an exothermic reaction. See how the reactants start up high? We put in a little bit of energy to get over that activation hump, and then whoosh, it's all downhill from there, releasing a ton of energy and ending with products at a much lower, more stable energy state.
And as you might guess, the journey for an endothermic reaction is pretty much the opposite. You still have to climb that activation hump, but this time you don't go downhill. You end up at an even higher energy level than where you started. The whole reaction is an uphill climb, and it has to absorb energy to make it happen. Okay, theory is great, but let's put it into practice. It's time to get our hands dirty, run some actual numbers, and calculate the final energy score for a real reaction. This is where we solve the mystery for good.
And you know what? It's a really simple 3-step process. First, we just add up all the energy it's going to cost to break the bonds in our starting chemicals. That's our energy in. Second, we add up all the energy we get back when the new bonds form. That's our energy out. And last, we just subtract one from the other. Easy.
So the case we're going to crack is this one. A molecule of hydrogen gas reacts with a molecule of chlorine gas.
What we're trying to make is 2 molecules of hydrogen chloride. So think about what's happening. We have to break one HH bond and one Cl-Cl bond. And in return, we get to form 2 new HCl bonds.
Now, to do this, we need a cheat sheet. This table here gives us the bond energy for each bond. Basically, it's the price tag. It tells us how many kilojoules of energy it takes to break a certain amount of that specific bond. These numbers are going to be our guide.
All right, step 1, let's calculate our total investment. How much energy do we have to put in? Well, we look at our table. Breaking that hydrogen-hydrogen bond costs 436 kilojoules, and breaking the chlorine-chlorine bond costs 243. Add them up, and our total energy investment is 679 kilojoules.
Perfect. Now for step 2, the payout. How much energy do we get out? We're forming 2 new hydrogen-chlorine bonds. The table says forming one of those releases 432 kilojoules. Since we're making 2, we just double it. That gives us a total energy payout of 864 kilojoules.
And now, for the moment of truth. Let's tally up the final score. We take our energy in, which was 679, and we subtract our much bigger energy out, which was 864. And the result is negative 185 kilojoules.
And there it is. Because the final number is negative, it tells us that our payout was bigger than our initial investment. The reaction released a net total of 185 kilojoules of energy into the surroundings. Our calculation proves it's an exothermic reaction. It's going to give off heat. Mystery solved.
You know, if you take just one thing away from this whole explainer, let it be this awesome little memory trick. In endothermic reactions, energy has to enter. And in exothermic reactions, energy exits. It's really the simplest way to remember the whole code.
So there you have it. You now have the tools to be a chemistry detective. Seriously, look around you. From the fizzing of a bath bomb to the simple flame of a candle, energy is being traded all over the place. Now that you know the code, what other everyday reactions can you explain? Something to think about. Thanks for tuning in.